think we have less than a minute to start. So I will just explain something before we start regarding participation. Again, Shabab, participation is measured by your engagement in the class. So you should have a microphone that's available at all time for you to answer questions or ask questions. The other thing is, like, for this course, again, this is recorded, so if someone is not here yet, he can go ahead and watch it. So if for this class, there are two reasons that you need to keep. There are two things that you need to keep in mind, or you should continuously review materials for two reasons. The first one is this is a fundamental course in electrical engineering, and whatever comes after this course will depend on it. So you may need to spend a good amount of time studying for this course. The second thing, because this course the second reason is this course is cumulative, meaning that what we cover today is what we're going to cover, inshallah, tomorrow will depend on what we cover today, and what we're going to cover, and day after tomorrow will depend on what we cover tomorrow. So the thing is, like, everything depends. There's some sort of like a chain dependence between topics. So you should keep that in mind. If you are busy, just spend like 10 to 15 minutes going over what we covered in the. I mean, you have to study on a daily basis. Just spend like 10 to 15 minutes going over what we've covered in today's class or in today's lecture. The second or the third reason is this is a summer semester, so we usually cover a week in the summer semester is equivalent to 2 weeks in a regular semester. So everything is condensed. Everything is we're moving in a faster pace compared to a regular semester. Okay, so starting with lecture 6, let me make a few announcements. The first one is homework 1 is posted, and it's inshallah due on Thursday at 11:59. For submission of the homework, please use a website called Gradescope. Gradescope, you can access it using the following link. And if you scroll down, you see an option for enrolling as a student, and you can use the course entry code. For quiz 1, it will be inshallah on Wednesday during class time. The material for that is 1.1 to 2.5. For the quiz, I posted an older quiz just to give everybody the same, everybody a fair chance. For those who had access to the previous quizzes, they might have a better chance, but I posted all previous quizzes. I taught this course once, and that's the quiz I posted from the last time I taught the course, or from the only time I taught the course before. Okay, so going over what we covered in the previous lecture. So if you recall, we studied Ohm's law, KCL, and KVL, and we stated that those three laws are the fundamental laws of this course. So if you master these three topics, you master the course. As simple as that. For Ohm's law, V equals to I multiplied by R. The plus or minus depends on the direction of the current flow with respect to voltage. And we saw that with Ohm's law, we can simplify the expression for the power. So power could be, the general expression is voltage times current, but if we have, using Ohm's law, we can express it as current squared multiplied by the resistance, or voltage squared divided by the resistance. And the second important law that we studied is KCL, Kirchhoff's current law. And we stated that for KCL, the sum of the currents in any node should be 0, which implies that the sum of the current entering the node should be equal to the sum of the currents leaving the node. And the last law that we studied in the last lecture was Kirchhoff's voltage law. And we stated that the sum of the voltage drop across, or voltage raise across any closed loop, or any loop, if we have a loop, it means it's closed. The sum of the voltage across any loop is equal to 0. And that's what we studied. That's the main those are the main topics of chapter 2. And by this time, I'm assuming everybody is strongly familiar with those. In this lecture, we're going to take a step further. We're going to deep dive into the notion of resistance. If you recall in the previous, if you recall last week that we introduced the notion of resistance in the context of applying Ohm's law. In this lecture, we're going to instead of talking about a single resistance, we're going to explain, or we're going to talk about the combination of resistances. For that reason, or this is a natural occasion, or this is a natural situation, because oftentimes you're not interfaced with a single resistance, but instead of that, the thing that you're seeing is actually the combination of multiple resistances. This combination could be in series, or it could be in parallel, or it could be neither. So it could be neither a parallel nor a series. And for each, if we have a series combination of resistances, or a parallel combination of resistances, then there's some shared criteria that are going to help us simplify the analysis. So let's start with the series combination. We can say that two resistors are in series if they are connected to the same node, and that node has only two elements. Taking an example here, let's think about node B here. So node B connects R1 with R2. So R1 and R2 are connected to the same node, and this node only has two elements, nothing more. So compared to the following situation, if I have the following node, I call this one R2, this one R3. So we can say here that R1 in series with R2, or R1 in series with R3, or R3 in series with R2. Even though they're connected in the same node, but this node has more than two elements, has three elements. So it's very important that they are connected to the same node, and that node has two elements. So you may ask yourself, what are the implications of that? And we studied that in the previous lecture. We said that if we have a series connection, then those resistors, if we have two resistors that are connected in series, two or more, and then those resistors have the same current. Think about it this way. Let's talk about node B. So if we apply KCL here, hold on, Ahmed.
السلام عليكم دكتور.
Yes. A question?
Yes.
Okay.
دكتور.
Hold on. أحمد.
Yes.
وقف شوي اصبر.
Okay.
At node B, so applying KCL at node B, we can see that if we apply KCL, we have two currents, and both currents are entering that node. So we have minus I1 minus I2 equals to 0, or this implies that I1 equals to I2, a negative I2, which means that the current I1 will enter, if we assume that the current I1 will be entering the node, the current I2 should be leaving the node. So this implies that R1 and R2, they have the same current. And we can say the same about R2 and R3, R3 and R4, R4 and R5, R5 and R6, R6 and R7, which implies that all of these 7 resistances or 7 resistors have the same current. Ahmed, your question?
Yes, you have answered my question.
Okay. Please hold on to your questions. So we need to move with the material that we should cover. Excellent. Okay. So let's take it a step further here. Let's analyze it mathematically. Let's represent the entire circuit here with a single element, meaning that let's represent the entire circuit here with just a voltage source and a resistance that's equivalent to the combination of all of these resistors. To do that, what we need to do is we need to apply KVL here. So let's apply KVL. Let's assume that we are moving in the clockwise direction. So we are moving here. So if we apply KVL, then we will get minus Vs plus Is multiplied by R1. Again, we concluded from the previous slide that I1 equals to negative I2, and if we continue with this derivation, we'll see that all of these resistors have the same current, and the current passing through each resistor is Is, which is the same as the current generated by the source here. So if we apply KVL here, we get Is multiplied by R1 plus Is multiplied by R2 plus Is multiplied by R3 plus Is multiplied by R4 plus Is multiplied by R5 plus Is multiplied by R6 plus Is multiplied by R7 equals to 0. So if we take Is as a common factor, and let's go here, Is as a common factor, we see that we have Is multiplied by the summation of all of these resistors. So we can say that the summation of all of these resistors is the equivalent resistance. So meaning that we can say that, we can so the voltage between A and H is equivalent to the product of Is with, with R equivalent. So it's equivalent in the sense that the voltage, if we apply Ohm's law, then the voltage between A and H will be exactly the same as just applying the Ohm's law on the equivalent resistance. If you sum all of these voltages, V1, V2, V3, V4, V5, V6, V7, you will see that the voltage here, the summation of the voltages, V1 to V7, is equivalent to the multiplication of the current with the equivalent resistance, with the summation of all resistances. So from that, we conclude that the equivalent, if we have a series combination of resistors, then the equivalent resistance is going to be the summation of all of these resistances. So any question before we proceed?
It's clear.
Okay, very good. So we consider the first case. Let's move to the second case. The second case is what happens if we have resistors that are connected in parallel. And let's see what happens here. First of all, two or more resistors are in parallel if they share the same pair of nodes. So if you connect two resistors, if they are in parallel, it means that these two resistors, or more than two actually, it's not necessarily two, these two resistors must share the same pair of nodes, meaning that must share the node from the top and node from the bottom. Consider, for example, this situation. Here we can say that R1 and R2 in parallel because they are connected, they share the same pair of nodes. So they share a node A and they share node B. However, for example, here, if I say this one R1, this one R2, this one R3, and if I call this one A, this node B, this node C, we cannot say that R1 and R3 are in parallel because they don't share the same pair of nodes. Even though if you look into the circuit here, they look kind of like in parallel, right? And in a circuit diagram, but they don't share the same pair of nodes. What happens actually is the series combination R1 plus R2, the equivalent resistance of those R1 plus R2 is in parallel with R3. So what's the implication of that? I will come back to your question. What's the implication of that? The implication of that is parallel resistors must have the same voltage. Because remember, the voltage is a potential difference. If they share the same pair of nodes, so we're talking about the potential difference between node A, the top node, and node B is the bottom node. So if they share these two nodes, it means that the potential difference between the upper node and the lower node is exactly the same. So that means that they have the same voltage. Any question? Okay, very good. So let's apply KCL here. Let's try to apply KCL at this node, node A. We have I1, I2, I3, and I4. And the reason for this application is the equivalent resistance can be found from applying KCL at node A. So let's apply KCL here. So KCL will be what? Anyone wants to volunteer? Okay, so Ibrahim. Ibrahim. Okay. Omar, Saleh.
Yes, Doctor.
Yes. Go ahead.
We can take positive for leaving and negative for entering the node.
Which is what?
So negative IS plus I1 plus I2 and plus I3 and finally plus I4, all equal to 0.
Exactly. Or I can write it like this. IS equals to I1 plus I2 plus I3 plus I4. Okay. From this, we can actually derive the equivalent. From this, we can actually derive the equivalent resistance. And let me just copy this one. Take it with me to the next slide. Okay. So what is I1 from Ohm's law? We can see that I1 from Ohm's law is Vs divided by R1. Similarly, I2 from Ohm's law, Vs divided by R2. I3 from Ohm's law, Vs divided by I3. I4 from Ohm's law, I4, Vs divided by R4. So you can see that the currents are given by this formula. So we have I1, I2, I3, and I4. So we can use this equation. Is equal to I1 plus I2 plus I3 plus I4, which is this equation. Then substitute. So we can take Vs as a common vector, and then we'll have 1 over R1, 1 over R2, 1 over R3, 1 over R4. So this combination here is 1 over the equivalent resistance. So the system now, the circuit now is reduced to a single resistor that captures the contribution of all individual resistances, meaning that we have something like this. So this is Vs, and this is the equivalent resistance. And the equivalent resistance is given by this formula. 1 over R equivalent equals to the 1 over the summation. Or you can state that R equivalent is okay. Talal?
Yes, doctor. I3 is Vs over R3, right?
Yes.
Because it's here written O4.
Yes. Very good. Ahmed?
دكتور الحين الار ايكوال تساوي مجموع equivalent اقصد تساوي مجموعهم مجموع الارات.
No. R equivalent will be given by this formula here. So you take the inverse of each individual one, then you sum the inverse, and you take 1 over the resistance, 1 over each resistor, then you sum this 1 over that resistor, then you take the inverse of that.
Okay.
Thanks. Okay. There was another question. Okay. So the situation could be simplified if we have two resistors in parallel. So if we have two resistors in parallel, something like this, you have R1, R2, then the equivalent resistance will be the multiplication divided by the summation. So you can derive it from the following. You can derive it like this. So 1 over R1 plus 1 over R2 equals to R2 plus R1 divided by the product. And remember, this is 1 over R equivalent. So if you want to get R equivalent, so you need to take the inverse of that, which is yes, Omar. Yes, Omar.
Yes. Dr. Will there be a formula sheet for this course?
Not for this part, maybe for the later parts, but not for this part.
Okay, thank you.
The cream?
Doctor, this formula only for 2 resistors?
Only for 2.
Okay, thank you.
So if you, yes, it's only for 2. So if you need to, if you have more than 2, then you need to use the general formula. So you need to actually use the following form, this one. Then
Okay.
it will give you 1 over R equivalent, then you take the inverse of that, and this will give you the R equivalents. So now if we can, if we use instead of resistance, we use conductance, then the equivalent will be simply the summation. So you have 2 options. The first one is you convert everything to conductance, then you sum all of the conductances, and in this case you will get the equivalent conductance. The inverse of that is the equivalent resistance. So you have 2 options. So oftentimes it's much simpler to do that because in most cases we have calculator, and for calculator the inverse is not that complicated. Ziad?
For the point of conductance in series, do we sum the resistance and then have the reciprocal for that?
If you have conductance in series, then you need to investigate it a little bit more because you need to derive it. First of all, if you have resistors in series and you use the conductance, you are wasting your time because the equivalent resistance for each of them is going to be the summation of all of them. So this method in paper simplifies the calculation of R equivalent when you have a large number of resistors connected in parallel. You get my point here?
Yes.
If you have a conductance, if you have a series combination of resistors and you want to get the equivalent conductance, then you need to do the inverse. But if you're going to use it, it will give you 0 because you are wasting your time, even though you're going to get a correct answer. So it's very important that it's very important that you are efficient when it comes to calculation. Okay. Let's pause and summarize what we did so far. And let's talk about some comments. Let's comment on the equivalent resistance here. So remember we had 2 situations, so we did not consider the last situation, which is a neither situation, because there's no simplification that we can make. So if we have resistors in series, we said that we can have either series or parallel combination. So if we have series combination, the equivalent resistance will be always greater than the largest resistance of the combination. Why is that? Because if you go back to, or if you recall, the equivalent resistance for series is going to be the summation of all the resistances. So the equivalent resistance must be greater than the largest resistance in the combination. So if you have 2 and 3, then the equivalent resistance will be greater than 3, which is 5 in this case. If you have a parallel combination, then the equivalent resistance is less than the smallest resistance in the combination. This is very important. If you have, say, like 2 and 3 connected in parallel, and you did your calculation, and you notice that you got the equivalent resistance to be 4, for example, then definitely you're making a mistake. Because for a parallel combination, the equivalent resistance must be less than the smallest resistance. This is assuming that we have finite resistance, non-zero resistance. Now let's take it a step further. Let's assume that you have a resistor that's in parallel with a short circuit. So for a short circuit, we have the following situation. So this is R1. Well, let me call this one R. This is a short circuit. So if you have a resistor with a short circuit, first of all, the resistance of a short circuit is 0 always. If you have a resistance that's in parallel with a short circuit, then the equivalent resistance will be 0. So the equivalent resistance will be short circuit. There are 2 reasons for that. There is a physical explanation behind this, and there is a mathematical explanation behind this. So let's imagine that we have a resistor that's in parallel with a short circuit. Then the equivalent resistance will be R1 plus R2, R1 multiplied by R2, R1 plus R2. Let's assume that R2 is a short circuit, which means that R2 is 0. So the equivalent resistance is 0 here, which is again a short circuit. So this is the mathematical explanation. The physical explanation is the following. For currents, it always prefers the path with least resistance. So at this intersection, the current has 2 options. One is to go through the resistor, the other one is to go through the short circuit. So the current will choose the path through the short circuit. And this makes actually R not necessary. So no current is passing through it. So we can easily remove it. So the equivalent resistance will be short circuit. Now, what happens if you have, yes, Omar?
Sorry, by mistake.
Okay. Now, what happens if you have a resistor in parallel with an open circuit? So if you have a resistor in parallel with an open circuit, so the open circuit is given by, can be drawn like this. So what is the resistance of an open circuit? So the resistance of an open circuit is actually infinity. Why? Because remember the definition of resistance. Or resistance is the material capacity to resist the flow of charges. So if you have an open circuit, it means that charges cannot flow. So the impedance or the resistance for that is actually infinity. So if you have a current here, and the current has 2 options. One is to go through the open circuit, the other one is to go through the resistance. So the path with the least resistance is actually this path. So simply the open circuit does not change anything if we have a resistor in parallel with the open circuit. You can prove it mathematically by applying L'Hopital's rule. Yes, Abdullah.
Yes, Doctor. What causes the short circuit? Did we cover it?
What's your last name, Abdullah?
ما سمعت.
What's your last name?
حسن العبد الله.
Hassan Abdullah. Hassan, can you go back to your question? What was it?
What causes or what is a short circuit?
What else a short circuit?
Yes. It's a resistance or like I think it's
If you have a cable, for example, and you connect the cable between two nodes, then that cable is considered a short circuit, ideally.
Okay.
So a short circuit in a sense that you're giving. So think about it this way: a resistance is a path where you have it's longer, in a sense that the charges has to be, or the current is going to encounter some difficulties. Short circuit is a shorter path to move between node A and node B without encountering any difficulties.
Okay.
Doctor, I think the best explanation that having switch, if the switch is off, then we can say it is an short circuit.
No, if the switch is on, we can say that it's a short circuit. If the switch is off, it's open circuit. So we need to.
Yes.
Very good. Now, so we're done with the parallel combination, and the series combination is kind of redundant. In this case, if we have a resistance that's in parallel with a series with the short circuit, it means if you have R1, then a short circuit, and you're talking about the equivalent resistance here will be simply the resistance. If you have a series resistor, you have a resistor in series with an open circuit with an infinite resistance, then the equivalent resistance will be infinity, because if you have something like this, let's say that then Ix here will be 0, so no current will flow here because it's an open circuit. So the current at this junction, for example, or this node, let me call I1, will have two options. The first one is to go through R2, and the second one is to go through R1. The current will always prefer to go through R1 because R2 is a path with the with the highest resistance. Okay, so any question before we start the example? The Karim, question?
Yes, doctor. What happens if I have multiple short circuits? Will the current flow through one or through all of them?
What happens if you have multiple of them? We're talking about equivalence here. So multiple of them, you can combine them as an equivalent. If you're talking about in a practice, then one of them, then the current will be circulating. If you're talking in practice, so one of them will have less resistance than the other. So in practice, you won't have like a short circuit. Okay. You will not have a pure short circuit. But here, if we're talking about the circuit diagram, then we're talking about equivalency. So if you have them, if you have multiple of them, so you should have one of them. Ziad?
In the first figure you draw, the current would prefer to go through the cable that doesn't have a resistance, right?
Yes.
So if you put an emitter next to the resistance, it would read 0, right?
Yes.
So the question, how does electrons or the current knows the presence of that resistance without going on that path?
You have to ask the current. I don't know.
Okay. maybe to go and then go back?
No. The current will never flow. So the thing is, like, we're always think about the methods that we're using, or the analysis, or the explanation that we're used is kind of like a simplified version of what's going on in a microscopic level. So if you recall in one of the lectures, I believe in the second one, we're talking about, we're always assuming that the current is flowing similar to water flowing from one point to another, right? But the actual mechanism is not like that. So we have drifting. We have drifting of current. Going back to your question and thinking about it as from a water flowing analogy, if you have kind of like a river or valley or something like this, and there are two paths. One of them is a down. One of them is a steep down. One of them is steep up. How do you know that? How the water knows that it should not go through the steep up? Does it have to try and see if it's?
Okay.
It's going to be the same if we're thinking about it in terms of a water flowing analogy, but in the practice there's some microscopic actions that takes place. Munir?
Doctor, if I have first question says, what's the R2 resistance? Can I say it's infinity?
This one?
Yes.
No. The R2 is going to be exactly the same as the value of it.
Clear. Thank you.
طيب اوكي هذا منير صح يسأل؟
إيه سعد خلاص.
Okay, in this case, so let's go ahead and start the exercise. So in this exercise, we have IS, I1, and I2, and we need to find those. So we need to use what we know about combining resistors in series and parallel to help us simplify the circuit. So far, the circuit that we have consists of one loop. But now, since we are familiar with the combination of resistors, we can actually expand, or we can actually complicate our circuit. So let me just copy this one, and we'll start with Abdullah Bajneed, like just in a minute.
عبد الله
عبد الله كلكم عبيد الله ما يعرف. So before we start Abdullah, let's try to find, first of all, in my opinion, the best way to do that is to divide the tasks. To finding, I can start with finding I1, I2, then IS. So, but in order to find I1, I need to find V1. So let's try to find V1. So if we want to find V1 Abdullah, what should we do?
بس دقيقة معلش دكتور مو أقدر الحين أطلع ال IS باستخدام أومز لو.
No. What's the fault because what's the voltage across the 4 ohm resistor?
120 فولت.
No.
طيب اقدر استخدم KVL.
120 is from this point to this point, not from A to X. From node A to
طيب
node
ما في الا انا بس ما في الا نود واحده بين الفولتج وال 4 ohm resistor.
Yes, they are in series, but if they are in series, it doesn't mean that they have the same voltage. If they are in series, it means that they have the same current. Okay, who can help me with, okay, let's see. Participated. Mohammed?
Yes, Doctor. Can I just find the equivalent resistor and find IS by dividing 120 over the equivalent resistor of all the resistors I have?
Yes, we can find IS by doing that. And that's what we're going to do. But I want first to find V1.
If I'm going to find V1, I might use KVL in the loop, but I think it's not going to work because I will have two variables, I1 and I2, or I1 and IX.
Okay.
In my mind, I just found the equivalent resistor and calculated IX.
Okay. Okay. Oh, you see that your approach is correct, but I'm looking for a specific approach for a reason, because I'm going to explain. Hadi?
I use the same method by finding the equivalent resistance and find the rest.
Okay. Right, sure. Adib? ما أديب عدنان.
نقدر نطلع الايكوفالنت ريزيستنس حقتها 6 و 3 نجمعهم كان على انه سيريز بعدين نجمعها مع 18 ونطلع الفي 1.
Okay, exactly. So not they are in parallel with 18. So let's simplify the circuit. So most of you, Shabab, they jump into the conclusion because I want you to go through steps, especially here. If you are to solve it like in a quiz or something like this, then it's okay. But here we're trying to explain to everyone, so I'd rather explain it in steps. Okay, so in this case we have 18 ohm in parallel with a series combination of 3 plus 6. So I have 18 ohm in parallel with 9 ohm, which is in this case the R equivalent will be 18 multiplied by 9, 18 plus 9, and this is going to give me 6 ohms. So now I have a simplified circuit, a little bit simplified, not completely simplified. So I have 120, then I have 6 ohms. So can I further simplify it? Okay, sure. الحمداني عزيز.
Yes, Doctor. You want to simplify the resistors?
Yes.
So, the 6 resistor and 4 resistor are in series, so we can add them.
Okay. So now I have the simplified circuit. I have 10 ohm. So just keep in mind what's the value just keep in mind that V1 now is missing. We'll get back to it. Now, what's the current? Back to the questions. So the first two explain what's the current. So let me, Yasser.
Yes, we can use Ohm's law and find the current, which is 120 divided by 10, which is 12.
12 amperes. So this is from Ohm's law. Okay, now what is V1? So this is still IS. So it's going to be exactly the same. Abdullah al-Jariri.
Yes, we use Ohm's law. It
Okay.
multiply 12 times 6.
Okay.
The current versus the resistor.
Okay. And this is going to give me 72 volts. So now let me go to the entire circuit here, the full circuit, which is this one. So what is I1 now? Let me look for a new name. Ahmed Al-Hamid.
It's V over R, which means it's 72 over 18.
Okay, 72 over 18, which is 4
Yes.
amperes. Ohm's law. Okay, now I have two options to find I2. Who can give me the first option? Okay, let me look for a new name. Abdullah Nas.
I can use KCL.
You can use KCL. Exactly. So if you use KCL, can you explain to me how to use KCL in this case?
IS will be equal to I1 plus I2.
IS will be I1 plus I2. So I2 will be IS minus I1. IS was 12, I1 is 4, so this is going to give me 8 amperes. Okay. طيب. What is the other option? Who can give me? Okay, let me look for a new name. Muhammad Abdulaziz.
Yes, Muhammad Abdulaziz Suwail.
Go ahead.
The equivalent resistor of the two resistors in series 3 and 6 will have the same voltage as the 18.
Okay, exactly.
So it will have a resistance of 9 and a voltage of 72, so it's 8 ampere.
Okay, this is from Ohm's law, exactly. So we can see that we have two options. The first one is to use KCL, the other one is to use Ohm's law and the series combination. And you can see that by inspection that the current will be doubled in the second branch, because the equivalent resistance here is half of the equivalent resistance in the first branch. Okay. So let's move on to the second exercise. Yes. Yes.
بس إذا ما عليك مجال سلايد.
I have to move fast. طيب.
Yeah, but just a simple question. Let's say, for example, if there is no for resistance.
طيب. Can you hold on? Can you keep your question until the end, because
okay.
we need to finish a specific topic.
Okay.
Same goes for Abdulaziz as well. So keep your questions, please, until the end. طيب. Okay, so the second exercise is asking us to simplify this, the following circuits, and we have 4 of them. I'm not going to solve with you all of the 4, but I'm going to solve with you the first one. I'm going to post a solution for the remaining 4. So starting from the first one, or starting with the first one, so we have a bunch of resistors. Some of them are in parallel, some of them are in series. And we want to combine them. And in my opinion, the best way to approach this one is to draw step by step. So let me start with Salman.
The 45 and the 30 are connected in parallel.
Yeah. Those are in parallel. What else in parallel?
What?
What else in parallel?
The 15 and the 60.
Okay. So I have 15 and 60 in parallel, and 45 and 30 in parallel. So 15 parallel with 60, and this is going to give me 12. And 45 in parallel with 30, and this is going to give me 18. So I can simplify the circuit now. I redraw it. It will be 25, 12, 50, 18 ohm, 20 ohm, and I have 10 here.
Doctor, you changed the locations of the 12 and 18.
Okay. It shouldn't matter when it comes to the calculation, but yes. Okay. This one should be 12. This one should be 20. Okay, very good. طيب, I'm looking for Mahsen.
Yes, the 18 and 12 and 20 ohms resistors are in series.
Okay, very good. The 18, 12, and they are in series. Okay. So the series combination will be 50. So I have 25, 50 ohm. You have 50 ohm, and you have 10. So for 15 parallel with 50, what should be the equivalent resistance here? طيب. Looking for شباب who from those who raise their hands, who hasn't participated? Mohammed, I included you. طيب. Okay. طيب. Okay, let me see. Ibrahim, Shaib. Yes, Ibrahim.
Yes, we can find the equivalent resistance for the 50 and the 15 parallel.
Yes.
It will be 25.
Yes, if you have 2 resistors, they are the same value, and they are in parallel, then the equivalent resistance will be half of that. So it's going to be 30 then you have 25, then you will get 25 here, then you will have 10. So what's left here is the series combination of all of them. So you will get 30 volts plus 25 plus 25, 50 plus 10, which is 60 ohm. So the equivalent resistance here is 60 ohm. And you can see here the steps that we use is actually we start, we don't jump into conclusions. So we start step by step and we tend to draw the circuit each time. This is going to give us like a better visualization to the circuit that we have. The second part is asking us to find the power in each circuit, or the power delivered by the source. And this should be very simple here, because we know this value, we know the voltage across the equivalent resistance, and we know the equivalent resistance. So the power will be V squared divided by R. So V is 30 squared divided by R equivalent, which is 60, and the power is 15 watts. Okay, that's what we have. The remaining parts I'm going to upload the solution, and I encourage you to solve them, so you can get better understanding. Okay. Ali? Ahmed al-Nafi. Okay. Good. Right. So let's move on to the second part of this lecture, and this part is talking about voltage division. So what happens is in many circuits that you have is you're going to have a different voltage level. So some components, some ICs will have specific voltage level, say like 5 volts. Others have others that are operate at 3.3 volt. Some might operate at 1.5 volts, etc. So you have multiple voltage levels. So you have one of two options. The first one is actually to assign battery for each individual, assign source for each individual component. So the 5 volt component will have its own battery. The 3.3 volt component will have its own battery, and so on and so forth. But this is not a practical way, because batteries usually bulky, and sometimes they introduce some sort of noise to your circuit. So you want to avoid having, imagine that if you want to change all of them, one of them is dead, so you need to change it. Then the next day the other is dead, you need to change it. So it's not a practical from a maintenance point of view, and it's not practical from space point of view, because you want to minimize the space that your circuit, your practical circuit, is accommodating. So a better option is to use a resistive circuit. The resistive circuit, you have a bunch of resistors. They are connected in series, and this connection will ensure that depending on the value of these resistors, you will have different voltage levels. So this is a better option, but not the best option. The best option will be using a nonlinear circuit, which is going to be the topic of E203. So let's, in this course, let's focus on what happens if we have a resistive circuit. So if we have a resistive circuit, let's imagine that we have the following scenario. So we have a constant source, say like this one is 5 volt battery or 3.3 volt battery. And you want to find what will be the voltage across R1 and what will be the voltage across R2. So in order to do that, let's find the current I here. And from that current, we can conclude, we can deduce the value of V1 and V2. So let us first find I using Ohm's law. So in order to find the current using Ohm's law, so I need to combine R1 and R2. They are in series, so the equivalent resistance will be R1 plus R2. The total voltage will be Vs. Again, this one is Vs divided by R equivalent. Now let me apply Ohm's law again to find V1. So I know the current passing through V1 is I, which is the same current here, multiplied by R1. So this is gonna give me Vs R1 plus R2 R1, or I can write it this way, V1 R1 plus R2 multiplied by Vs. Similarly, V2 is going to be I multiplied by R2, Vs divided by R1 plus R2 multiplied by R2. So V2 will be R2 So this is a very important conclusion here. Because think about it this way. This one is equivalent to saying that V1 is a constant alpha multiplied by Vs. V2 is a constant beta multiplied by Vs. So by adjusting these values, alpha and beta, by finding, say, for example, if you want to take the output across, if you have, say, one component is taken, for example, let's see, trying to think about numerical value. Vs is 10 volts, for example, then you want to get 7 volts and 3 volts. So forget about the numerical values. I cannot think about any numerical value here. So the moral of the story is the following. So we have, by adjusting the values of R1 and R2, we can have different voltage levels. And this is very important because imagine in this case you have a load. A load is something that an external load or external circuit that you have a circuit and you want to connect it to another circuit. So that other circuit is considered a load. It's not part of your original circuit. It's not part of your original circuit. It's something external, and that's why we call it a load. So the load could be anything. It could be an electric circuit, for example, an IC in your cell phone, or it could be a motor, which is a non-electric component here. So what happens is, in this case, if you want to connect your output, if you want to take the output of your circuit to from R2, then in this case, the output will be proportional to R2. And it will be, again, a function of the load. So the output here will have a component that's part of your internal circuit and a component that's part of the load. Notice that you want to, if you have a practical circuit, then you want to eliminate the dependence of your voltage level to the load. What it means that if you remember when we talked about ideal voltage source, what did we say about them? What did we say about ideal voltage source? Fahim?
That they don't depend on other variables.
Exactly. If you have 10 volt, then it's going to be 10 volt. But in this case, imagine that if you're taking V output, and V output depends on R. So imagine that this is your ideal voltage source, or everything here is your voltage source, and those are the points where you connect your voltage source to your external circuit. Then, just by looking into the expression here, you see that your voltage source depend on the load. So you want to reduce this dependence. So you cannot avoid it. You cannot eliminate it. End of story. So you cannot eliminate it with such a circuit. So you need to play with your components here, with your resistance, to ensure that this output does not depend on the load. And you can do that by ensuring that the ratio of R2 divided by RL is approaching 0. So in this case, V output can be assumed as the following: R1 So you can see here that the output does not depend on the voltage source and on the load resistance. So this is the motive behind dividing the voltage, having different voltage level for different resistance, or designing a circuit that's going to give you different voltage level for different resistance. So we can take this exercise, and I don't know if I have time to do that. We have 3 minutes. Okay. So let's take this. Let's start with this exercise, and if we cannot finish it, then we'll continue next time. For this exercise, we have a voltage divider resistor, and we assume that the tolerance of each resistor is 10%. What do we mean by that is the following. In a practical scenarios, you don't have an exact resistor. You don't have 25 kilo ohms. But you have 25 kilo ohm with a specific tolerance, meaning that plus or minus 10, it means, or let me talk about the 100K, because it's easier mathematically. So for 100 kilo ohm, you don't have exactly 100 kilo ohm. So you have 100 kilo ohm resistor, but it could be anything between 90 kilo ohm and 110 kilo ohm. So this is the case of 10% tolerance. You see that in other scenarios, you have a 1% tolerance, meaning that your resistor can be any value from 99 to 101 kilo ohm. So the lower the tolerance, the more expensive the resistor it is. So what happens is you want to design a voltage divider circuit, but you don't know about your components. You don't know about the values of these components. So the values of these components could be anything within 10% of these called the nominal values, 25 and 100 kilo ohm. So you want to calculate the voltage swing. What do we mean by that is, what will be the range, or what will be the maximum voltage and the minimum voltage that you can achieve within the tolerance of your entire circuit. And I don't believe we have time for that, so I will continue. I will solve this exercise inshallah next time. And that's it for today. Yes, Abdulaziz.
So the maximum value of the V naught will be when the resistor's maximum.
Not really. You will see that the maximum value is when R2 is maximum and R2 is minimum. R2 is maximum and R1 is minimum. So what happens is the following: you have a bunch of resistors. If you buy a resistor from a factory, from manufacturer, you see that they will say that those resistors are 20 or 100 kilo ohm. But if you measure them with a multimeter or with the ohmmeter, you will see that they're not necessarily 100 kilo ohm. So if the tolerance is 10%, you might face a resistor that's 90 kilo. So if you are designing a voltage divider circuit, so usually you design more than a single element. So just because of this non-ideality, you will see that you will have different voltage level. And you will see that when we solve this exercise, we'll have the maximum voltage that we can get is 83, and the minimum voltage we can get is 76. So there is a 6-volt difference between the maximum and the minimum. Okay. أحمد.
دكتور أنا عندي سؤالين. السؤال الأول ممكن تروح السلايد اللي قبل هذه.
This one?
Yes. Doctor, can I say the relation between RL and R2 is parallel?
Yes.
But what about if the voltage is?
And this is going to. This where we get.
Yeah, but the voltage if passing through R1 and it comes into R2, it will be different, isn't it?
The voltage
matter just between RL and R2.
No, RL and R2 they have the same. They are in parallel. So that means they have the same.
Okay, Doctor. There is another question, but it's in the. Could you please go back?
Is it in this one?
Yes, yes. Let's say, for example, if R 4 ohm is not here.
Yes.
Is V1 equal to 20?
Yes.
120 volts.
Yes.
Because they are in parallel.
Yes. If the 4 ohm resistor is not there, then the V1 will be 120 volt.
Okay, thanks.
طيب عبد الله عبد الاله.
اي دكتور، الحين بالنسبه للواجب احل في ورقه خارجيه بعدين انزل في جريسكوب.
يس.
والكويز بياخذ حصه الاربعاء كامله ولا وقت معين؟
I don't know. I haven't written the quiz yet. I'm not worried about for the quiz. I'm not worried about the actual time of solving the quiz. I'm worried about making sure that everybody has the right setup for that quiz. Ziad?
For the last question, the divider of the voltage, is there a certain way to know which to increase by 10% and which to decrease from the resistors?
Is there a certain way of knowing which one to increase and which one to decrease? What do you mean by that?
Don't we increase the resistors and decrease it to find the maximum and the minimum?
No, no, we're not here to increase or decrease the values of the resistor. We're here to get an idea about what will be the voltage level. So I'm giving you this resistor. You're buying this resistor from Amazon, for example, and it says in the label it's 100 kilo. Okay, and you're happy about it. So like, okay, I bought 100 kilo resistor. Then you went to the lab and you measure the resistance for that, and you notice that it's 90 kilo. And say like you bought 10 of them. So only one of them was 100 kilo. The other ones could be anything between 90 and 110. So if I ask you to design, for example, a voltage divider circuit, and that voltage divider circuit is supposed to deliver 80 volts. And you notice that, well, I have 80 volts. I want 80 volts. But due to the fact that I have non-ideal resistors, I found that, well, I can tolerate anything from 76 to 83. So if I buy if I get these resistors, I should be fine. However, for example, if you notice that, or if you know that in your application you cannot afford going below 80 volts by 1 or 2 volts. Then if you want to purchase these resistors, you should look for a value of a tolerance that's much less than 10%, say like 1%. The price that you might end up paying will be almost double or 3 times. So that's the reason for studying such a circuit. Is it clear?
Yes. And is the voltage between R2 and the V0 equal the same thing?
The voltage between R2?
Yeah, across R2 and V0.
Yes, it should be. The voltage will depend on the value of R2.
Yes.
If you have 100 kilo ohm, then the voltage will be different from having 90 kilo ohm or having 110 kilo ohm. Think about if you're buying bins, for example, and you can tolerate anything from, say, like pink to orange, which kind of like you're kind of like in the red region, for example. Then you can buy like cheap bins with different colors. However, if you're thinking about buying, if you need exactly a red bin, then you might end up paying extra money for that because you need exactly an exact color.
I see. Thank you.
Abdullah Hassan Al-Yusuf.
Doctor, I have a question about the first question you have solved.
This one?
Yeah, yes, this one. الحين دكتور لما حسبنا الفولتج عند ال4 اوم كيف ال 18 و6 صار كلهم نفس الفولتج؟
لا 18 6 مو كلهم نفس الفولتج. 18 و9 نفس الفولتج.
18 و9 طيب وش السبب؟
if you draw it this way, you'll get صح?
صح.
Okay, why 9 and 18 they have the same voltage?
Because they are in parallel, so
Yes.
of the same voltage.
Okay. Does that answer your question?
But they parallel with the 120, not
They're
72.
not in parallel with 120.
They are not?
Yeah, they're not sharing the same pair of nodes. So 120 is connected between this node and that node. While, for example, the 9 and 18, they are connected between this node and that node.
So if we replace the voltage source with the 4 ohm, just imagine.
The voltage source of the 4 ohm?
Yes.
No, they will not be in parallel. The only way for them to be in parallel if the 4 ohm is removed.
الحين ما استوعبت ليش نفس قيمة الفولتج حق اللي حسبناه مع التيار الأول.
No, in this case, what is the condition for parallel combination?
They are sharing 2 terminals.
2 nodes, right?
Yes, 2 nodes.
So for 18 ohm resistor, so you agree that 18 and 9 they are in parallel?
Yes.
Okay. So for the 18, for the 18 ohm and the 120 volt, do they share the same 2 nodes?
Oh, I get it now. I got it now.
Okay.
Thank you, Doctor.
Ali?
Doctor, in the exam, can I solve with the method in chapter 2? Or
what are the methods in chapter 2?
I make the I equal to I1 plus I2, then I make a third 3 equations.
Oh, you apply KVL?
Yes, yes.
You can do that. You can, as long as you solve it, you end up with the same solution.
Yeah, I got I1 is 4, I2 is 8, and IS is 12.
Yeah, okay. There are multiple. There's not a single way of solving the circuit. The reason for doing that is we're trying to explain a basic concept behind something related to today's topic that we're trying.
Okay. Okay, Victor. Another question in the fourth, in the question that you solve that contain 25 and 48. I think the third example.
This one?
Yes, yes. How do you know where to start to simplify the circuit?
Okay. How to know? So let's look into the simplest possible, or simplest possible process. So let's go to part B. So if you just look into this circuit, which parts are simpler than the other?
The kernel that contain 18 and 12 is easy to us.
Yes.
Some.
They are in series, صح?
Yes.
And
the 20 and 60.
Yes. So you can start with those.
Yeah.
Then if you combine this in series, you see that the series combination will be in parallel with 60.
Yeah.
And if you combine 60 with the series combination, you will see that it's going to be in series with 30.
Yeah.
And so
it depends on where is the current is flow, or
Yes, it depends. It depends. Usually, you start with the
parallel.
usually start with the middle.
Yeah.
The middle is kind of always complicated.
Okay. Thank you. The last question is about I tried to solve some question in the chapter 1 in the book, but there is something with unit conversation that we didn't cover, or is it in the exam like bound or pixel or?
No. Don't worry about it.
Okay. Thank you, Doctor.
Okay, we'll see you inshallah tomorrow.